Okay, so I'm hoping that everybody has already downloaded what they need. So for Pilot, you just go to the geodynamics.org website and download the binary for your platform. And I'm going to go, it just takes a few seconds to install it, hopefully, although I know that Noel had some problems. And then for Qubit or Trellis, if you're um, a government agency, you can get Qubit from Sandia National Laboratory. Otherwise, for the purposes of the tutorials and also for the workshop coming up, you can get a 30-day free trial of Trellis from csimsoft.com. So that's for the meshing. And then finally, for visualization, you can download ParaView for free. So just download that for your platform. So I'm hoping that everybody has these, but if you don't, you might want to do that very soon. So what I'm going to do, first of all, I'm going to I've already downloaded the binary for the platform that I have, which is a Mac running Mavericks. Then I'm going to install that, set it up, make sure that I can run a test problem. And then we're going to go to some of the 3D Hex8, or well, we're just going to run really one of the 3D Hex8 problems. So I'll go through the various steps that we need to do that. So first of all, let me do that. And I want to share my screen. So what I want to do, I want to make sure, first of all, that, so can we see this terminal here? Can you see it, Brad?
Can see it move. Can you make it bigger?
Okay.
And your font bigger?
Yep. Oh, did that not work? You bigger. Tell me when it's big enough. Is that big enough?
One more big.
All right. How's that?
That should be pretty.
Okay. And is the whole
Can you
thing
make the
fitting?
window bigger?
Okay. It's hard for me to tell how big to make it.
That's good.
All right. Okay, so I've downloaded the tarball here, which is just this. So all I'm going to do is expand that in the directory that I've selected. Oh, got one of my disks is waking up. Okay, so now we'll change to that directory. And the first thing we're going to do, there's a setup.sh file here. So if you're running bash or sh, you can just source this, and it's very simple. All we're doing is we're setting your path to include the path to PyLith. We're setting your Python path appropriately, and also the path where you load your dynamic libraries. So I'll just do that. So now that's where this particular version of PyLith is installed. So to make sure that you can run it, then try going to examples 3D Hex8. So you'll see this is the directory where we're going to be working today, and it's got a bunch of example problems which are described in the manual. Also, they're briefly described in the README. But just to make sure you can run PyLith, just type PyLith, then try step01.config. And so you can see it ran. You can see it solving your equations here, and then you get a bunch of output. We don't see any errors. So then when I did that, it created output, and we'll go through that later. But the first thing we're going to do, the steps in running a simulation involve, first of all, you decide on your geometry, and then you create a mesh that describes that geometry. So that's the first thing we're going to do today. Unfortunately for me, my trellis, they've updated the license just this morning, so it doesn't work on my Mac. So I'm going to do it on my Linux machine here. Okay. So we're going to go to the mesh directory. And the way you control trellis or qubit is with various journal files. So we have here a separate geometry.journal file, which we'll look at. And then with qubit or trellis, you can call one journal file from within another. So if you look at our mesh journal file, you'll see that the first thing we do is play back our geometry journal file. So if we look at that, we'll just look at it briefly, and then we'll step through it in trellis. So this is an incredibly simple problem where we just have a box, and then we're, first of all, we're going to split that box with a vertical surface, which is going to be our fault surface. And then we're going to split it horizontally with another surface that is going to divide the box into the upper portion and a lower portion. So I think the easiest thing is we'll go into trellis. So let me get that over here. Tell me, is that too big?
That's perfect.
That fits. Okay, good. So now in Mac, I know you almost every time you start trellis, you have to set your directory. So that's the first thing we're going to do. So we'll go to File, Set the Directory. In this case, we're already where we need to be. So we'll just choose that directory. And this will be the directory where the mesh journal files are. So we choose that. Then we're going to open up here the journal editor. And we're going to open up the geometry.journal file. Now let's see, can I make this, I probably need to make that bigger. Not sure how to make it bigger. There must be a way. I'm not seeing how to do it. Can we see that okay? That journal file?
Yeah, it's sort of small, but I'm not
Yeah.
sure. I can't remember how you adjust the font.
I can't remember either. I should have looked that up. Let me just look real quick.
Why don't you just keep going forward, Charles?
Okay. Okay, so the first thing we're going to do is create our box. Here it describes the dimensions, and here's where we're doing it. We're using the qubit brick command. So we just do that. We've made a box. So there it is. Then we want to move the box so that the upper surface is at z equals 0. By default, the coordinate center is at the center of the box. So we're going to move that box down. So we'll translate it. Okay. Then we're going to make our fault surface, which is just a vertical surface coincident with the x equals 0. So we do that. There it is, right there. Now we're going to make a horizontal surface coincident with z equals minus 2000. So here we do that. Okay, so now we have the components of our geometry, but right now this box doesn't know anything about the surfaces. So to do that, what we have to do is what we call web cutting. So the first thing we're going to do, we have our box is volume 1 over here. We're going to web cut that with a sheet body, which is the first one is body 2. That's our fault surface. So we'll do that web cut. And what that does, it divides the volume into 2. And then once we do that, both of those 2 sides of the volume will know where the connecting surfaces are. So first we'll divide it with the one that we've called fault surface. Okay, now you can see that we have 2 volumes. Okay, now we're going to divide volume 1 with the material interface. That's the horizontal surface. So we'll do that. Now you see we have 2 surfaces here, or 2 volumes. Now we're going to do the same thing for the other volume. So do that. Now we have 4 volumes, and we're going to name those. So the upper right volume we'll call elastic xpos, the upper left elastic xneg, and then so forth. So the bottom we'll call visco. So here we're going to name all of those. Okay, so now you can see that they have names, not just volume numbers. So once we've done that, we will imprint. Imprint lets one volume know what surfaces are attached to it, and then you merge them so that any coincident surfaces or curves get merged together. And then at the end, we're going to delete these 2 sheet bodies that we don't need anymore. So first we'll do the imprint. Okay. Oops. Sorry about that. And then we will do, I'll merge and then delete those 2 bodies. Okay, so here we are. We have our different volumes. We can draw each volume separately if we want to examine it. You can look at the surfaces that make up that volume. You'll see that some of them are named because we cut them with a named surface. Then continue like that. So we've created our volume. The next thing we have to do is then mesh it up. So I'm going to open up the file where we do our meshing. So now we've already done this part. We've created the geometry, so I don't have to do that anymore. So when we're creating a mesh, the first thing we have to do is let Qubit or Trellis know what size of elements we want to do. And in this case, we've decided on a size of 1,000 meters. So, and also by default, the meshing type is hexate. You can specify tetrahedral elements if you want, and frequently we do that. But in this case, we'll use the default hexahedral volume. So we'll set the size, and then we'll mesh the entire volume. So there we go. That's meshed the whole thing into nice cubes. And then what we want to do, for Pilot, we have to have material blocks that let us know what material to associate with each block of elements. So volumes 1 and 4, which are our top two volumes, we're going to form those into one block, and we're going to give that block a name of elastic. And then similarly, the bottom two volumes, we're going to give it the name viscoelastic. So we'll have two material blocks when we finish here. So we'll do that. Okay, so now what we have an elastic block, which is all the cells in the upper volume, and then we have a viscoelastic block, which is all the cells in the lower volume. And these block IDs will be used within Pilot when we're specifying materials. Okay, then we have to start creating what we call node sets, and these are sets of nodes that define groups that are used within Pilot for faults, boundary conditions, and things like that. So the first one is to add all of the nodes in the fault surface. And, okay, so let's look at these. So we have, let's draw this volume. Okay, so we want, also, right now we want to select surfaces rather than volumes. So here, this surface is called fault surface. Now, if we go down to the bottom volume, we can draw that, and we'll see that it has one called, let's see, is that still, this is fault surface at A. Yeah, there we go. So what we want to do for both of those surfaces, we want to take all of the nodes in those two surfaces and make them into a single node set. So that's what we're doing right here. First, we add the nodes in fault surface, and then we add the nodes in fault surface at A. And then we're going to first make a group out of those. Now we have a group. We have one now called fault. So that's all of those nodes. Then we want to make that group into a node set, and that's what we're, oh, sorry, we already did that here. Now we have this node set, but we're going to then give the node set the name fault. So now if we look, now we have a node set named fault. This information will be exported with our mesh, and that's information that will be used by Pilot. Now, this is optional. We're not making use of this yet, but we may at some point make use of what they call side sets. I'm just going to do that right now. I'm not going to talk about that because we're not actually using it right now. Now, then we're going to go through all of the different surfaces to which we might want to apply boundary conditions, and we're going to create a node set for each of those. So we're going to create one for the positive x side right there. We'll do one on the negative x side, and similarly for y, and then for z. So we'll do these x plus, minus, y plus, and minus, z minus. We'll do those. So you'll see now that we have all of those are groups, but we also have new node sets, and those are what is going to be exported. So there's our fault, x positive, which is over here, x negative, y positive, and y negative. Then we have z negative. Now the one thing about this, you remember that our fault comes all the way through, so it intersects this z negative surface. Now in PyLith, we can't apply boundary conditions to a fault surface. So to deal with that, what we do is we'll create a node set for that boundary that does not include the nodes in the fault. And that's what we're doing right here. We're creating a group where we first add all of the nodes that were in Z negative. We do that. So if we look at this group, right now it includes all the nodes on the bottom boundary there. But now we're going to remove the nodes in the fault. So that's what, that's what we're doing here. So now if we look at that again, you'll see that it includes all of these nodes, but it doesn't include the nodes in the fault. And so now we're going to create a node set that is just those nodes. All of the bottom nodes except for the ones in the fault. There we go. And then finally, we're going to create a node set for the top face. And we're not going to apply boundary conditions there, but we are going to output our displacement solution there. So we do that. And now, so now we've defined all of our nodes. That's our final one right there, the top surface. And then the final thing we have to do is export the Exodus file, which we're calling the file box_hexate_1000M. So we'll export that. Okay, so now that we've done that, you'll see that we've created this box_hexate .exo file right here. Now, if we wanted to, we can visualize this, but we've already looked at it in Qubit or Trellis, so I think I'm going to pass on that. So are there any questions about the meshing before I continue on to the setting up the problem part? I can't tell that there are.
I don't see any evidence of typing.
Okay, then I'm going to quit out of Trellis. What I'm going to do, I'm going to switch back to my Mac. So when we run PyLith, typically we'll have one or more .cfg files, and associated with the problem, we'll usually have one or more spatial database files. So I'm going to start first with the config files. The first one that we want to look at is PyLithApp.config, because this is a file that's read by default anytime you run PyLith. If it sees a PyLithApp.config file in the directory where you're running, it will automatically read that. So I've opened up over here. Should I increase the font size? Or is that okay?
Go one size bigger if you can.
One size bigger. Let's see. Is that better?
That's better.
Okay.
That's good.
So for all of the problems, here I'll switch back for a minute. All of these problems in here, the way you're going to run them, you'll type PyLith, and then whichever one of these we want to run. In this case, we're going to be running step03.config. But for all of these, it will by default read what's in this PyLithApp.config file. So that's what we'll look at first. So it's kind of hierarchical the way it works. So the very first thing you'll see at the top is PyLithApp. And then everything else will be kind of down the chain from this top level. So the first thing we have here is some journal information. And all this does is tell the various portions of the problem whether to be verbose or not. And so we're telling the PyLithApp top level to give us information, the time-dependent problem to give us information. We don't have Green's functions in this case, but then the implicit solution will print out information. PET-C will, the linear solver will, mesh.io, etc. So that's just how much information to show while we're running the problem. So the first thing we have to do is get a mesh in. So all of these problems use the same mesh, and they're all generated by Qubit. So the first thing we do is tell it that our mesh generator, the reader, is the Qubit mesh.io. So it's Qubit. By default, it assumes a hex8 problem, so we don't have to specify that. But what we do have to do, so the mesh generator reader, we have to give it a file name. So the file name is the mesh that we just generated, which is in the mesh subdirectory, and it's called box hex8 1000 meters.exo. So that is the Qubit mesh that we're going to be reading. So once we have that, then we can start looking at our materials. So we're going to divide our materials into two. Our mesh has two material IDs. And so in PyLith, we're going to call these upper crust, which is our top part, and we're going to call it lower crust. So here we tell it what names we're giving. And these are just names that we're giving within PyLith. We're calling it upper crust, lower crust. Then down here, we specify the information for each of those. So for the upper crust, what we're doing, first of all, we're giving it a label. We're calling it upper crust material. Very descriptive. Then we're saying that the ID for that material is 1. So what that means is that the Qubit ID that we had, which was block number 1, is going to be associated with the material upper crust. And then we're going to also associate a spatial database with this material. So first of all, we give a label to our spatial database. We're just going to call it properties for the upper crust. And then we have to give it a file name. And this, I'll get to the file later, but this will be in the Spatial DB subdirectory. And within that subdirectory, there's a file called mat_elastic.spatialdb. We'll look at that in a minute. But this will specify the elastic properties for this problem. We also have to give quadrature information for each material. And so A hex 8 element is a Lagrange element, so we give the cell quadrature to be Biot Lagrange. Biot is what we use for our quadrature information. So we give it the type of element, and then we give it the dimension. This is a 3D problem, so it has a dimension of 3. So we've done that now for the upper crust. Now we'll go down to the lower crust, and we do exactly the same thing. The only thing that's different here is that for the lower crust, we associate the that with the block ID of 2. So this is the trellis block ID that we described for our mesh. And then we give it a different label, but we're going to use the same material property database. And as you'll see for these, it's just a constant material properties. And again, we have the same quadrature information as we did before. And then the final thing we do is set the solution options. These are our PET-C solution options. And these are kind of our very basic default parameters that we use for PET-C. Let's see, by default, the malloc dump, I'm not sure what that does, if that is automatically set to true or false when we leave it blank like that. We have the important thing here, we have our preconditioners. So this is kind of our default stuff. We have an ASM preconditioner type. You have to set a shift type. And then we have our convergence parameters here. This is for the KSP linear solution. We have a relative solution tolerance of 10 to the minus 10. We have an absolute tolerance of 10 to the minus 20. We're going to allow a maximum number of iterations of 100. And then this is the PET-C GMRes. It restarts every 50 iterations. I think it would take too long to go through what all these mean in detail, but these are kind of basic default settings. We're going to monitor the solution. Let's see, I think usually we want to view the solution, so I'll go ahead and set that so that we can view the solution. We'll have it tell us why it converged, and we'll have it give us an error if it does not converge. You usually want that because if your solution doesn't converge, there's usually some kind of problem. The nonlinear options we're not using for the problem we're looking at today, so we'll ignore those. And then finally, we want a summary of everything that happened while we ran. So that's usually a useful thing to have for performance, things like that. So I'm going to save that. Now, the particular problem that we're looking at is step 03. Oh, where's my little thing? Oh, that's not what I wanted to do. Oh, okay. Yeah. Oops. Right. Okay. So what happens is when you give it a config file on the command line, all of the options in the command line config file either supplement or overwrite the options that were in the PyLithApp.config file. So these are additional solution parameter or additional simulation parameters that this particular problem needs. So the problem that we're solving, this is a very simple problem with a vertical fault. We're going to give it mostly left lateral slip and a little bit of reverse slip. So, and it tells you at the top of each of these how to run the simulation. Here's how you would run this one. So the first thing we're going to do is tell it how long to run. So this is a static problem, so it's only going to run for a single time step. So it's zero time static solution. You can give it a time step size, but this is kind of unimportant for a static problem. The next thing we have to do is to provide it some boundary conditions. So the first thing we do is tell it that we're going to have 3 boundary conditions. Right here, we give it an array and give them names. So the boundary conditions are xpos, xneg, and zneg. So we're going to constrain the positive and negative x boundaries, and then we're going to constrain the bottom of the mesh. Similarly, we tell it about our faults. We're going to have a single fault in this problem, so the array only has a single entry. So interfaces equals fault. We're just going to call our fault interface fault. And the next thing we're going to do is to tell it where we're going to provide solution output. So we're going to provide it, we're going to have 2 output managers. One is for the entire domain, the other is for the subdomain. So first of all, we give it the array of the output managers, and then by default, it will output the solution for the entire domain, so we don't have to do anything for this one. But for the subdomain, what we have to do is tell it to output for a solution subset. And further down, we'll tell it what subset to output for. Okay, so the next section here are our boundary conditions. So we're going to give it the simplest possible boundary conditions, which are just 0 displacement boundary conditions on the positive x and y boundaries, as well as the z boundary. So first of all, we're going to tell it which degrees of freedom to constrain for each of those. So for the positive x boundary, we're going to constrain degrees of freedom 0, which is the x direction, as well as degree of freedom 1, which is the y direction. So the z degree of freedom will remain unconstrained on this boundary. We're going to name this, give a label. So we're going to call this space xpos. And then the database label, we're going to also give it, because by default, it reads a, by default, it applies the 0 displacement boundary condition, but you still need a label for it. So we're going to call it DirschLabelC, which is displacement boundary conditions on plus x. And then we do the exact same thing for the negative x boundary. So exactly the same, we're constraining x and y. We give it a label name for the actual boundary condition, and then we give a label for the database.
Charles, remind people that the label is the node set in qubit.
Oh, yep. Okay. This label is, yes, the node set that we defined in qubit, if you remember, which you probably don't. We gave it this exact name in qubit. If you give it a different name here, it won't be able to find it and you'll get an error. Okay, now for the bottom boundary. So this is the z negative boundary. We're going to constrain just the z direction, which is degree of freedom 2. Now here is the special node set that we defined in qubit, which is space zneg no fault. So what that is, that's the node set that includes all of the nodes on the bottom boundary except for the fault. So what would happen if we were to try to apply it to the entire boundary, we would get an error because we would end up trying to constrain a node that is on the fault. So instead, we're using this special node set that we defined. And then again, we give a label to the database itself. Okay, so those are our displacement boundary conditions that we're applying. And then we're going to come down here to our fault conditions. So the first thing we do, we've already said that we have a single interface called fault. The first thing we're going to do is describe what type of fault this is. We have a number of different types in Pilot. This is one called fault cohesive kinetic. And that means it's a type of fault where we apply static displacements or static dislocations along the fault. So then we're going to define the parameters for this fault. First of all, we tell what the label is. So this is the node set in qubit, as it's mentioned right here, that this is the fault node set that we defined in qubit. So we tell Pilot that that's the node set that defines the fault. Now, since we have to integrate over the fault, so that means we have to give it quadrature information. And again, the cell type is Fiat Lagrange, since it's a Lagrange cell. But in this case, the fault surface is just two-dimensional. So our quadrature cell dimension is 2. So there's our quadrature information. And then this particular type of fault, we have earthquake sources and we have a rupture slip function. And so what we first give it a label. We'll call it final slip. And then in this case, we're defining the fault slip using a spatial database. And the file name for this spatial database, it's in the directory SpatialDB, and we've given it the name finalslip.spatialdb. And we'll go through these databases shortly. We're also, when you query a spatial database, we have two different options in Pilot. The default is nearest neighbor interpolation, where it will just grab the nearest value in the spatial database that it finds for and then apply that value. In this case, we're going to give it a linear variation so that we can have linear variations in our fault slip. And we'll see how this looks in the spatial database in a minute. And then finally, we have to give it a slip initiation time. For this problem, it's just going to be 0 since it's a static problem. But we define this slip initiation time in another spatial database, which has the name sliptime.spatialdb. So then the very last part is we have to give it where our solution information. So we have, if you recall, we had two solution output managers. The first one was for domain, and so that just outputs the displacement field for the entire domain. And all we have to do in that case is give it a file name for the output. So we're putting it in the subdirectory output, and it's just going to be called step03.btk. Now we have another one that's the solution just over the ground surface. That's our subdomain output. And we have to tell it which qubit node set corresponds to this subdomain. So this was our node set called face ZPOS. So that's a node set that we defined in qubit. And that tells it where to output this subdomain solution. And then for this one, we're going to give it the name step03 groundsurf.btk. So these two will have our solution for the displacement field. Now we also want to output our fault information. So in this case, it already knows the node set for the fault, but we have to give it an output file name. So we're going to give it the we're going to call it step03-fault.btk. So that's our fault output. Finally, we have to output our state variables, which for elastic materials just means stress and strain. And so we have separate ones for the upper crust and the lower crust. So first of all, we have to filter the results because for Hex 8, we actually have, in 3D, we have 8 quadrature points, and visualization packages can't handle that. So what we do is we average the solution and put it all to the center of each cell. So that's what this is doing. We're filtering, we're averaging the solution, putting it at a single point. And then we, for the upper crust, we give it this file name, Step03 upper crust. And then for the lower crust, we do it right, same thing. We just give it the different file name. So those are the config files which control the behavior and define the main parameters. If there are any questions about that, feel free to ask those now, because what I'm going to do now is move on to the spatial databases that we're using. Any questions there?
No typing yet.
Okay, so I'm going to go to Spatial DB, Mat Elastic. Let's see. Okay, so the first thing we defined, if you recall, we can just look here. If we look at PyLith app, the first thing we had was both of our upper and lower crusts use a spatial database for the elastic properties called mat_elastic.spatialdb. So in this case, we use pretty much the simplest possible one we could have. In PyLith, you have zero-dimensional variation, which is just a single point. You can have 1D, which would be variation along a line, 2D, which would be variation over a surface, and then 3D is complete variation within a volume. So in this case, we're using a 0D spatial database to give constant material properties for each material block. That means we just have to give a single point, and then that will give us the same properties for the entire material block. So they all look fairly similar. We have our stuff here, which the number of values is 3 because we give it density, BS, and BP for our elastic properties. We give it the names of these properties. And then we can tell it which units we want to use. In this case, we're using kilograms per cubic meter for our density and meters per second for our BS and BP. And then we tell it the number of locations, which is how many points we're using. That's just 1. And since we're only using 1, that means we have a data dimension of 0. So zero-dimensional variation within the volume, although our spatial dimension is still 3. We're using a simple Cartesian coordinate system. We're not doing any, we can, if we wanted to, we could change this to some factor if we wanted to specify our coordinates in meters or kilometers or anything like that. We could change that. And then again, our coordinate system has a spatial dimension of 3. So then this describes the spatial database, this whole section right there. And then below that, you just have columns, which include your X, Y, and Z coordinates. And then you have density, BS, and BP within each column. So here we're giving it density of 2,500 kilograms per cubic meter, BS of 3,000 meters per second, and then a somewhat higher BP, which I can't remember what this will transform to in terms of our elastic properties, but it'll be fairly normal Earth properties here. So that's very simple spatial database for our material properties. Now for our fault information, we'll have a slightly more complicated spatial database, unless there's a question about this one. No. So I'll open up. Okay, I think it's called vinyl slip. Is that what it's called?
I think so.
Yep. Okay. Okay. So in this case, we have a slightly more complicated variation because what we want to do, we want to vary our fault slip with depth. So to do that, in this case, we again have three values, and they correspond to our left lateral slip component, reverse slip component, and fault opening. And the units for all three of those are meters. But in this case, we're going to use 3 points to describe our vertical variation and the fault slip. That means that we now have a data dimension of 1, since we're varying the slip along a vertical line. Again, our spatial dimension is 3, and we have a simple Cartesian coordinate system. In this case, to make life easier, we're going to specify our coordinates in kilometers. So that's what this here, to convert to meters, you would have to multiply by 1,000. And again, our spatial dimension is 3. So now what we're doing, what we're saying, this is the surface of our mesh at 0, 0, 0. We have a left lateral slip component of 2. We're given a 0.25 meters of reverse slip. And then we're not going to have any fault openings. So we're not going to have, that would be if you wanted to have a dike or something like that, you could have fault opening. Then at 2 kilometers depth, we still have the same amount of left lateral slip, so that will go remain constant there. But now if you remember, in our config file, we specified a linear query type. That means that the reverse slip will now vary linearly between 0 kilometers and 2 kilometers depth. And then it will be 0 from there to the bottom of the mesh. For the left lateral slip, we'll have constant slip from 0 to 2 kilometers depth. And then it will vary linearly, or from 2 meters of slip down to 0 slip at the bottom of the mesh. So you could also, within the config file, tell it to use a nearest neighbor interpolation, in which case we would get a more jagged slip distribution. But in the config file, we told it to use linear interpolation, so we will get a more smooth slip distribution for our final result. So, any questions about the spatial databases? Hearing anything or seeing anything? Okay, so now all that remains is to run a problem. So, as I mentioned, all we do, PyLith, we're going to do step 03, and just for fun, it's not needed for this problem, but just for fun, we're going to run in parallel. So all you have to do for that sort of thing is tell it how many nodes to run on. We're just going to run on 2 nodes here. So this will partition the mesh and run it on 2 cores of my machine. Usually when you do this, you want to save a log file in case there's any problems. So in Bash, the easy way to do this is so you can just redirect everything, and we'll T it so that we can see it on the screen at the same time it's going to the log file. So we just do that. And so there it ran. And so once we've done that, we have output down here. So in the output directory, we've created a bunch of BTK files. So now the final part, I'm going to look at the results of our problem using ParaView. What? Oh, something weird just happened. ParaView will not open up. Well, okay. Well, we'll do that in Linux then. Okay. We'll just run it real quick. Okay. Is that too big?
Nope.
Okay. So we've got ParaView open here. And the first thing we're going to look is just at our main solution. This is your basic output, which is this step 03. Now, if you have BTK output, it gives you this T with all the zeros. That's your timestamp. If you had a problem that had multiple time steps, you would have a whole bunch of these for each type of output, and each one would represent a different time step. But since this is a static problem, we just have a single output for the single time step. So we'll open that up. So all you see is just your box here. But to make it more interesting, the first thing you can do is just color it by displacement. By default, you just see the magnitude of the displacement. But to make it more interesting, we can look at the different components. X component. We can also look at the actual cells. The Y component. There, you'll see the sharp. This is the along strike component. You'll see a sharp boundary there. Z component. So right there. Now, the other thing you can do, which is frequently useful, is you can look at the actually how the mesh deformed. So we'll do that. This is the warp by mesh or a warp by vector filter. So we can do that. We're going to warp the mesh by the displacements that it computed. So we'll do it by like 500. That's how much we scaled the displacements by, because otherwise you wouldn't be able to see anything. So now we can see how the mesh actually deformed when we ran this problem. So what you can see is we've got primarily left lateral placement and a little bit of reverse slip, which you can see right there. The other thing we can do is we can actually look at the vectors of how the displacement occurred. So to do that, we can use the glyph filter. We can do that. The default glyph type is arrow. We can go down here. It'll scale it by the vector. That's fine. And so then we'll apply that. So this shows you how the mesh actually moved when we applied the fault displacements. So yeah, you can see what happened on both sides of the fault. You'll notice that PyLith, the nice thing is that we do get actual separate movement on either side of the fault. So this, even though this point is coincident with this point in the mesh, in PyLith they get split apart, so we can see the movement on either side of the fault. We can also look at the stresses that we compute. So to do that, we'll open up. I'm going to open up both the lower crust and the upper crust at the same time. Apply. And then here, I'm going to turn these off. I want to treat these at the same time, so I'm going to select them both, and then I'm just going to group those two data sets. So anything I do will apply both of those together. So the first thing I can do is look at, that's the total strain, but we can look at the separate components. The XX component of strain, YY, the XY, which will give us essentially the shear in the XY plane. And then similarly, we can do this for our stress components. If we wanted to compute something interesting like the pressure field, which is something you might want to know about, a real handy thing is this calculator right here. So we go to the calculator. In this case, stresses and strains are at our cell data, so we have to switch. We're going to call our result pressure. And then we're going to compute it right here. So pressure is negative of stress XX plus stress YY plus stress ZZ, and then divide it by 3. Oops. So we'll do that. So this shows us our computed pressure for the problem. The final thing we can do is we can look at we want to look at the fault. We can open up the fault file. We'll turn off that so we can see. There's our fault plane. So here, these are the slip components that we applied. So that's the magnitude. X is the left lateral component, so you can see how we varied the left lateral component of slip. Y will be the reverse slip that we applied. You'll see that's a much smaller amount. And then, in addition to that, we can look at what the resolved tractions are on the fault as a result of applying that slip. So if we want to look at the traction change, that's just the magnitude. So the left lateral shear traction is given here. You can see that. And then the reverse shear traction is shown when you do that. Then finally, that's what we have at the fault. Frequently, we just want to know the displacements at the ground surface, and so that's what we have in our ground surface displacements here. So we have that, and we can look at our applied displacement. We'll have it show what this is our fault tractions. This is the displacements at the ground surface. And we can look at the different components. So this is the Z component of displacement. So actually there's plenty more you could show, but what I might do is stop there and see if there's any questions about this? Questions?
No evidence of typing. Oh,
I might have
how can I plot profiles?
Profiles. Okay. If you want a, there are many filters in, so ParaView, you can go to alphabetical. We can do plot over line. And now you'll notice that this is associated with the ground surface right here, since I had that selected when I selected the filter. So by default, it's chosen a diagonal line here, but you can move those around. But if we just wanted to plot a diagonal profile on the ground surface, you can do that. And now what we can see, and you can also show it which variables you want to do. So if we want to do, there's X, Y, and Z displacements. So there's that. If you want to, actually, the other thing you can do, you can also save the results from a profile, which you may want to do for future plotting on your own. You can do File, Save Data, and by default, it'll save that profile as a CSV, comma-separated variables file. We'll just call it step 03 prof1.csv. Whatever precision you want. This only has one time step, so it doesn't really matter whether we select that or not, but you can have it save a series of time steps for that same profile if you want. So we'll just hit OK. If you want, shoot. If we want to look now, and what that will have done, now you have this CSV file, which just has your X, Y, Z, and let's see, is that one? Yeah, X, Y, Z, okay, arc length, and then your X, Y, and Z coordinates. So there's how you can do a profile. Get rid of that, and I'll delete that profile. Any other questions?
So Charles, one question is about ASCII output that they can output in GMT.
I believe the simplest way to do that is using Python. It turns out it depends what type of GMT data you want. For instance, we haven't talked about this, but you can output point data from PyLith, where you interpolate the solution to a set of points, and that would be easily accessible to GMT. Usually, I think you would want to write a Python script to do post-processing to go to GMT. I don't know if we have an example of that. But if you wanted a GMT grid file, for instance, a GMT grid file is just a netcdf file. And so you can use, there's a netcdf package for Python, which I believe we probably installed that as part of the binary, right?
Yep.
Yeah. And so you have that. The BTK, actually, BTK we're not using so much anymore because most of the pilot output now we do with HDF5. And there's a nice package for Python called H5 Pi that lets you deal with the HDF5 files very easily. And so using a combination of that and the NetCDF4 package, I believe it's called for Python, you could easily go from pilot output to something that you could use within GMT. For instance, I don't know what people are wanting. If you're wanting GMT, you're probably just wanting displacements on the ground surface, I'm guessing. That would be pretty easy to do. You would just take your ground surface output, and if you were going to do that, actually, you could do File. You could save your ground surface data.
Well, I think
we'll call it.
This raises the question, Charles, you're jumping. So the question is sort of getting pilot data into GMT. The other issue is, well, maybe you're better off getting whatever else you have in GMT into something like ParaView. And so there's generally massaging input files like coastlines into ParaView accessible formats is what we've done. Because GMT doesn't have the 3D visualization capabilities that ParaView does.
Yeah, for instance, if I turn these up, I can open up, let me find,
While you're doing that, we also had a question about units in the output. All units in the output are the basic SI units, so meters for displacement, meters per second for velocity, and pascals for tractions and stresses.
Yeah. Yeah, what I use, for instance, this is really, I have a simple Python script to go from GMT to create a BTK file that ParaView can use for like coastline data. So this, I've done it for New Zealand. And so the nice thing, you can include this with any other visualization you have. So it depends. If you only want map view stuff, then, I guess you could translate PyLith to GMT. But if you want any kind of 3D stuff, then yeah, I think you should do what Brad says.
Any other questions? We're sort of a little over what our 2-hour estimate, but we're happy to take questions you have now. And we recommend that you continue to work through the PyLith manual, work through examples. If you have questions before the workshop, send them to cig-short@geodynamics.org, and we can answer your questions ahead of the workshop. We'll also be spending Monday and Tuesday of the workshop, working through tutorials, and there'll be time for one-on-one interaction, and much more time for questions. The idea of this is trying to get you over any lumps or difficulties you have getting started. So CIG has a YouTube channel, and so once we finish recording this session, I'll ask Lorraine and Eric how to transfer the video over to YouTube. It may take a day or so. Hopefully we can get it posted tomorrow. And we'll have a link to it from the agenda, and I'll upload the slides to there'll be a link from the agenda probably within the next hour. And we also recommend that if you're looking for additional tutorials, there's tutorials from last year's online tutorial session. There were 6 sessions of 2 hours each last year. That so you can use those to help you get started. Sort of a longer introduction and hands-on tutorials with slides accompanying them. There's some overlap of what we did today with the first introduction tutorial from last year. Any other questions?
Yeah, I would say continue through the 3D hexade examples. That's pretty, and play with them. You can mess with the config files. You'll probably get errors, but that's all educational too.
Last call for questions.
I know what I did.
Well, so here's just as a reminder, here's the CIG-short at geodynamics.org is the email address for the CIG short-term Crustal Dynamics working group, and that's where your questions will go to the community, and you'll get the fastest response going through that email list. Charles, Matt, and I monitor that sort of continuously, and we try and get back and answer the questions as quickly as we can. Most people wait less than an hour to get their questions. Some of the more complicated ones take us a longer because we have to find time to, go through and replicate people's errors and things like that.
I just figured out why Paraview and Trellis weren't working. Okay.
I have evidence of typing.
Is there? Oh, yeah.
Yeah, this presentation will hopefully be posted in the next hour. The slides will be posted, and then we'll try and get the video up either tomorrow or Monday.
Yep. Good. Well, everybody will be experts by the time we get to the workshop, and we won't have much to do.
We'll be able to discuss science.
Yeah.
Well, thank you everyone for participating. This is by far the most we've had for a pre-workshop help session, so we thank you for your questions, and we'll see you at the workshop.
All right.